Hi, everybody. Hope you're doing well. We're going to continue our discussion of solving systems of linear equations, but we're going to employ a new tool, one that you may have heard of, maybe not a big deal if you haven't. We're going to talk about what this new tool is and see how it works within the context of solving a system of linear equations. So if you're wondering what that tool is, I will tell you, it is a matrix. We're going to use what are called matrices to solve systems of linear equations. And while this may seem new and the arithmetic may seem tedious at times, it's actually a very clean method, and it works quite nicely when we go through the proper steps for essentially creating a new matrix that actually tells us what the solutions are, as you'll see in a few moments. So let's go ahead and get started. All right, so this is our introduction to matrices. Those of you that go farther in your studies, get into a topic known as linear algebra and beyond, you're going to spend some even greater time talking about matrices and matrix algebra and all the wonderful features they possess. But for now, we're just going to focus specifically on employing them for solving systems of linear equations. So to start with, why don't we, well, go back and solve a system of linear equations? And just to refresh ourselves on this process, right, I might call this equation 1. I like to label these so that I can keep myself organized. And we're going to solve this just the way we've learned up to this point. And so what I'm going to do is use elimination, or linear combination, as I actually prefer to call it. And so I think what I'll do, just because of equations 2 and 3 and the y terms, I'm going to get rid of y. So I'm going to take equation 2 plus equation 3. So what does that look like? Well, it's 3x minus 2y plus z equals -3. And then 5x plus 2y minus 3z equals 17. Okay, add these together, and I get 8x minus 2z equals 14, right? I'm adding these together. And I could go further and factor out a 2 if I wanted, right? So this would be 4x minus z equals 7. So I'm going to hold on to that. And then let's use, I don't know, how about 2 times equation 1 plus equation 2. And so when I do that, 2 times equation 1 will be 2x plus 2y plus 4z equals 0. And then we have a 3x minus 2y plus z equals -3. Add these. We have a 5x plus 5z equals -3. And so there's my second equation for my new system. So just like we expect, right, now we have a system of 2 equations with 2 variables. So let's look at these. We've got 4x minus z equals 7. And we've got a 5x plus a 5z equals -3. Maybe I call this equation 4 and this one equation 5, just to keep going. So now I think what I'll do is eliminate z. So I'm going to do 5 times equation 4 plus equation 5. So what does that do for me? That gives me a 20x minus 5z equals 35. And then I have a 5x plus 5z equals negative 3. So 25x equals 32. And so x is going to equal 32 25ths. I'm in business. That's good, right? And so now I can start back substituting. So I'm going to go back to equation 4 here. 4 times, 32 25ths minus z equals 7. Go ahead and solve this for z, and let's see, we'll have, well, I'll do this in all of its glory. So let's see, 128 over 25 minus z equals 7. So what is z gonna equal? Well, 128 over 25 minus, and then let's see, 7. So 128 minus 175, negative 47 25ths. That's my z. And then I can get my y, right? Go back to one of the original equations. So how about, so here I used equation 4. Now I'm going to use, I don't know, how about equation 1? So equation 1 is going to tell me that y is negative x minus 2z. So if you plug in what we got for x and y, what will we get? Negative x is 47. So negative 126 over 25. All right, and then I like to go back and just make sure that all my signs are good, which it looks like we are okay. So 35, that was 32, yeah. Okay, so there we go, linear combination method. Well, as we're going to see, we can also use a matrix. So what is a matrix? Well, it's a rectangular array of numbers. It's got rows and columns. The dimension of that matrix, of any matrix, is m by n. M is the number of rows, n is the number of columns, and then we label the entries according to location. So like the subscript aij means whatever entry is in the ith row, jth column, okay? And so if I gave you a matrix, let's say, and we often use either brackets or these big parentheses. So maybe I have 3, 4, negative 1, 2, 5, 0, 9, 1, 7, 6, negative 1, 8, okay? And so you'll see parentheses, or you might see brackets. Either way, you'll see me use parentheses. That's my preference, but it's not uncommon for others to use brackets. And you'll even see by different texts, they use different, they vary as well. There's no standard agreed upon notation. So, okay, so here, this matrix, the dimension of this matrix, well, it has 3 rows, right? 1, 2, 3, and it has 4 columns. oops, 4 columns, right? 1, 2, 3, and 4. So we say the dimension is 3 by 4. And then for the entries, the entry in, say, how about 2, 3. Now, when you read that, you don't want to think 8 and then 23. That means row 2, column 3. So row 2, column 3 is going to be 9. Okay. The entry in row 1, column 4, first row, fourth column, is 2. Okay, and so on. We could keep going with that, right? All right. Well, a coefficient matrix. A coefficient matrix is formed by taking the coefficients in a system of linear equations and forming a matrix with it. We can add a column of what those individual equations are set, expressions are set equal to, right? Like something x plus something y plus something z equals some constant. If we make those constants their own column, we add that column, we get what's called an augmented matrix. So let me show you what I mean by this. Let's take this set of equations that we started with and already solved. And let's see, 3x minus 2y plus z, and 5x plus 2y minus 3z equals 17. Okay, so the coefficient matrix I get that by taking my coefficients. So notice my first row here represents my first equation, right? My coefficient of x is 1, like x, y, z. In my first equation, my x coefficient is 1, coefficient of y is 1, and coefficient of z is 2. So 1, 1, 2 is my first row. Second row, 3, negative 2, 1. And then why don't you guys think about what the third row would be and write it in right now while I'm talking, blabbing, making small talk as you fill in row 3. Hopefully, well, shoot, here we go. Hopefully you said 5, 2, negative 3. Okay. And so what you see is each row you can see is the coefficients of the respective x, y's, and z's. And then each column is all, like the first column is all the coefficients of x. Second column, all the coefficients of y. Third column, all the coefficients of z, and so on, okay? Now, if I want to make this what's known as an augmented matrix, then I'm going to take my coefficient matrix, 1, 1, 2, 3, negative 2, 1, 5, 2, negative 3, and I'm going to add that last column here, okay? And so you can see, now these dash marks aren't actually part of the matrix, but you can see that the way this matrix then relates to my system of equations, right? Row 1, x plus y plus 2z is equal to what? Oh, it's equal to 0. That term in the or that value in that last column, first row. Okay. All right. Now we can do things with these rows. They're known as elementary row operations. We can add a multiple of one row to another. We can multiply any row by a non-zero constant, and we can interchange any two rows. Okay. And that's going to come in very handy. All right, so let's take a look here. I'm going to perform elementary row operations on this, okay, until I can actually get to my solution. So I'm going to start with, well, 1, 1, 2, 0, 3, negative 2, 1, negative 3, 5, 2, negative 3, 17. Now, let's look down here in this third row. If I could do things to this, so perform some operations to where eventually my third row is 0, 0, 1, and then something, then that third row would tell me what z is, right? Because I'd have its coefficients, right? 0x plus 0y plus 1z equals, I don't know, whatever that is. So I would know what z is. If my second row looked like 0, 1, and then, I don't know, something, something, then I could plug in what I learned about z, and row 2 now is just an equation of one variable, that variable being y. And then for row 1, well, from rows 3 and 2, I'll know z and y, so I can plug those into my row 1 equation and figure out what x needs to be, okay? So that's the game plan here. So I'm gonna actually erase some of this, and we're gonna go back to the beginning. But this is my goal. I'm trying to get to a matrix that looks like this thing I put in a box, okay? That is quickly going away. All right. Now, what I like to do is I like to keep track of what I'm doing. And I do that through these arrows. So if my first goal here is to turn, I don't know, the numbers between 1 here, right? I need to turn that 3 into 0, and I need to turn that 5 into 0. So what I'm going to do is I'm going to multiply, I'm going to start with the 3. I'm going to multiply -3 times row 1, and I'm going to add to row 2. Now, which row in my matrix am I actually changing? I'm changing row 2. So I'm going to circle it just to remind me that that's the row I'm actually changing. So row 1 stays as it was. Row 2 now is going to change. So I'm going to get 0 here. And then again, come back to row 1. So I'm looking at my second entry. -3 times 1 is -3 plus -2 is -5. 2 times -3 is -6. -6 plus 1, -5. 0 plus -3 is -3. Okay. Leave row 3 alone. All right. Well, now I want to get rid of 5. I want to turn that 5 into a 0. And so to do that, I'll do -5 times row 1 plus row 3. And I'm changing row 3. So row 1 left alone. My new row 2 left alone. And now I'm changing row 3. So I get a -5 plus 5 is 0. -5 plus 2, -3. 2 times -5, so -10 plus -3, -13. And then -5 times 0 is 0, plus 17 is 17. Okay. Next thing I want to do, remember, I'm trying to get zeros, or I want to be able to look at my third row and figure out what z is. And so I'm going to turn this -3 now into a 0. And so to do that, I'm going to come over here and I'm going to say, all right, how about, well, gosh, now things get tricky, right? So we have a choice. I need to use row 2, right? If I used row 1, I'd be, that 0 that I've got as my first entry in row 3 wouldn't stay 0. That's counterproductive. I want to move forward. And so you could do one of two things here. You could say, gosh, I really don't like working with fractions. And so you could look at, let me change my color. You could look at this -5 and this -3, and you could find some common multiple and use those to add. And sometimes that's easier. Nothing wrong with that. In fact, that's what I'm going to do. But keep in mind that really, at the end of the day, you could also just as easily just go ahead and use the fractions. It's not a big deal. So what I'm going to do is recognize that, right, 15 is a common multiple. So we're going to do -3, right? I need opposite signs. So we're going to do -3 times row 2 plus 5 times row 3. And it's row 3 that's getting changed, okay? So 1, 1, 2, 0, 0, -5, -5, -3, 0, and here we go. So 15, well, I'm sorry, 15 minus 15 is 0. And then we have 15 plus 5 times -13, right? So let's see what we get. So, sorry, 3, so 15 and then we have 65. So I've got a -50 here. And then don't forget, -3, right? We're changing row 3 here. So -3 times row 2. It's -3 times -3 is 9. Okay. So 9 plus, we get 94 there. So look where I am, right? At this point, I know what Z is, or at least I can almost find it. And I could then find Y and then X, okay? So let's do just that. To do that, I'm gonna make my life a little simpler to start. I'm gonna combine two steps here. I want my first entry in each row to be 1, so that I just have that coefficient of 1. So for row 2, I'm going to multiply by -1/5. And row 3, -1/50. Okay, and I'm going to change both those rows. So there's row 1, and then we have 1, 1, 3/5. And then for row 3, 0, 0, 1. And then 94/50 is 47/25. Okay. And so row 3 tells me that Z equals 47/25. Well, now, so I've got one of my solutions. Let's look at row 2. Row 2 tells me that Y plus Z is 3/5. So Y plus 47/25 is 3/5. And so what do we get for Y? Well, and oh, you know what? This was a -47/25. Sorry, guys. So -47/25, -47/25. And so Y is 62/25. All right. And then I'm gonna pause real quick and go back to my first slide, because I think I missed that negative over there as well. So sorry about that. Yeah, see, -2Z. So this Y should have been 62/25. 25ths as well. Okay. And now let's grab our x. So x, right, this is row 1. So row 1 tells me x plus y plus 2z equals 0. So x will be negative y minus 2z, which is, well, we know what y is, right? And we know what z is. So sorry, guys. Okay. So x is 32/25. All right. Okay, what we just did as a fancy name. It's called Gaussian elimination after a 19th century German mathematician. Okay, famous, one of the most famous mathematicians. And what we did was we turned that matrix into what's known as row echelon form. The first non-zero entry is 1, and which is known as the leading entry. All the rows, each leading entry of each row is to the right of the leading entry of the row above. So everything to the left of those leading entries would be 0. Okay, and then we could also put this in reduced row echelon form if we essentially turn it into this, where you have 1s on the diagonals and then 0s everywhere else. Okay. And then you got whatever that last column is, okay? So that's a reduced row echelon form, okay? So let's try that with this. Let's put this in row echelon form just for practice, okay? And so I'm gonna play that same game here. 5, 2, 3, 1, 2, 1, 7, 2, 3, 4, 5, 4. Okay, so remember my goal is to get this, my leading entry is 1. And so to start with, how about we make just zeros where we want them. So I'm gonna turn this 2 into a 0, all right? And so if I take 2 times row 1 minus 5 times row 2, and I'm changing row 2. So row 1 will stay the same. And then, right, now I'm gonna multiply the top row by 2, the bottom by 5, and subtract. So 10 minus 10 is 0, mission accomplished, right? And then we're gonna have a 4 minus 5, negative 1, 6 minus 35, negative 29, and 2 minus 10, negative 8. I didn't do anything to row 3, so we have this, okay? All right, next, let's make this 3 a 0. So to do that, I'm going to take advantage of row 1 again. I'm gonna say 3 times row 1 minus 5 times row 3. Okay, so we have 5, 2, 3, 1, 0, negative 1, negative 29, negative 8. And then here we go. 15 minus 15 is 0. 6 minus 20, negative 14. 9 minus 25, negative 16. And 3, 5 times 4 is 20, so 3 minus 20, negative 17. Okay. I'm getting closer. Next, I'm going to turn this negative 14 into a 0. And again, I'm going to do that. Well, I could take advantage of row 2. Okay, so let's take negative 14 times row 2 plus row 3. So row 1 is still 5, 2, 3, 1. Row 2, still the same. And then we're going to have 0, 0, and then let's see. So 14 times 29, 406, minus 16. So this one will be 390. And then 8 times 14. So 112, 17. This will be 95. Okay. So now we're close, right? I need those leading entries to be 1. So I'm going to do, whoops, come back. I'm going to do 3 things here. I'm going to take 1/5 times row 1. I'm going to take -1 times row 2, and 1/390th times row 3. So when I do that, my first row becomes 1, 2/5, 3/5, 1/5. My second row, changing the sign, and then my third row, and then 95 3/90ths is going to be what? Let's see. 1978. Okay. And so there we have it. I've got 1s in these 3 places, 0s to their left. I've got that row echelon form. Okay. Now we could go further, right? If we want Gauss-Jordan elimination, now we're going to turn it into reduced row echelon form. And so now, so let's go back to the system that we solved originally and put this in reduced row echelon form. Now I'm not going to reinvent the wheel, right? We did this already. We know what the solutions are. So let's go back and just kind of steal where we wound up. So I'm going to copy that matrix over here. All right, so where we wound up from that couple examples ago was we had turned this system into the matrix I'm writing here. Again, not going to reinvent the wheel. Okay. Now, what's nice about this is that, right, when we look at row 3, we know what Z is. Reduced row echelon form lets us look at every row and figure out what the individual variable is. So in other words, row 2, instead of 0, 1, 1, let's make row 2 0, 1, 0. And in row 1, instead of 1, 1, 2, let's make it 1, 0, 0. Okay? And so that's what we're going to do now. So the first thing is I am going to work with row 2. So I'm going to take negative row 3 and add it to row 2. Okay? And again, I'm changing row 2. So 1, 1, 2, 0 on top. And then I'm changing row 2. So we've got 0, 1, and then -1 plus 1 is 0. And then what do we get for, right, 47 25ths plus 15, there we get our 62 25ths. Okay, so what's happened now is you can see from rows 2 and 3 that I know what Y and Z are, right? Just by looking, because I've made the coefficients that aren't y or z respectively 0, right? Row 2 is 0x plus y plus 0z. How do we write that simplified? Well, it's y equals 62/25, okay? So let's do the same thing now with row 1. So for row 1, I'm going to take negative row 2 plus row 1, and that will give me 1, 0, and then 2, negative 62/25. Must be getting excited because my handwriting's getting larger here. Must be getting close to the end here. Calm down there, buddy. Okay. And then the last thing I can do is take, well, how about negative 2 row 3 plus row 1. And so when I do that, I'll have 1, 0, 0, 32/25. And then 0, 1, 0, 62/25, 0, 0, 1, negative 47/25. Okay. So that's matrices. Very, very brief introduction. And that's how we use them to solve systems of linear equations, okay? So at this point, what you want to be able to do is take a system, set it up in a matrix, augmented matrix, and use those elementary row operations to solve the system. Now, what remains is special systems, right? Because as we know, it's possible that a system has no solutions, or maybe it has infinitely many solutions. So in the next lecture, we're going to try to discern how those two special cases manifest in matrices. So in other words, a system that has infinitely many solutions, what does that look like in matrix form? Or if there is no solution, what does that look like? How does that turn up in a row reduced matrix? And so we're going to handle that next. Before we get there though, make sure you're familiar with setting up the matrices and working through those elementary row operations to get the right reduced echelon forms. All right, I will see you soon. And as always, seems like my sign-off phrase, happy studies.